All right, hi everybody, and welcome to our talk, which is going to be about system testing on hardware using OpenQA, and some other tooling as well, actually, but couldn't quite fit that into the title. So, by way of some introductions, my name is Laurence Urhegyi, and I work for Codethink. We're a services company in Manchester, and over the past 6 or 7 years, I've worked on various different automotive projects, and I've also worked on quite a lot of projects that are in open source projects as well.
And my name's Daniel Silverstone. I'm a senior consultant at Codethink. I'm primarily on the technical side rather than the management side these days. And I've been involved in open source for a significantly long time, possibly longer than some people have been alive. It's okay. Yeah.
Longer than I've been alive, maybe.
Oh, careful. So, given this morning's focus on virtualized testing, when everybody's talking about SDV and so on, this talk might feel a little bit odd, because we're going to try and talk a little bit more about hardware testing. But stick with it. You know, we're going to talk about why testing matters, a little recap of some of the ideas that we've presented in the past. I think we presented at FOSDEM and a couple of other places. And then we're going to move on to some of the advancements we've made since those presentations. So if you've seen us talk about some of this before, there is something new, I promise. And we're going to cover why we care about these things and how we feel that our work can help all of you to improve your testing situations.
Okay, so let's think about the landscape of automotive projects and the viewpoint that Codethink has and why we think testing is so important. So a lot of the talks today are about activities that are specific to AGL and progress in AGL recently and what's been pushed. This is a little bit different because it's more about how we view the automotive industry and some of the things that can happen within the automotive industry to improve testing, but I think a lot of it is very relevant to AGL. So in terms of software complexity, this was obviously touched on in the first keynote this morning, and I don't think that I have to labour the point really to an audience of people at AGL. Obviously, AGL was started in order to overcome some of the challenges faced by software complexity, but essentially the software that we're putting into the vehicle is getting more and more complex. I think I read that about 10 years ago, the average lines of code in a car was 10,000, and now, as Dan said this morning, AGL IVI is 111 million, and the cluster is 80-something million, so you're looking at 200 million lines of code. So obviously it's exponentially more complex. And there's an article here from McKinsey, which summarizes it quite nicely. I won't read all that quote out, but it's basically saying that the cost of integration is very high, and the features that customers expect, it's getting harder and harder to do full system upgrades so that people are keeping up to date with the latest features, and it's actually quite daunting. So we've added that statement. Most automakers are not set up to support the software for the life cycle of the vehicle, and full system upgrades are quite rare and avoided. And it's a bit of a sweeping generalization. I know people are working quite hard to improve the situation, but generally I think those statements are true. And if you think about the car that I drive, it's going to be on the road anything between 10 and 20 years, maybe longer, but I know for sure that the software will not be updated after 3 years. It might get a security patch, a critical security patch or a really important bug fix, but it's just basically keeping it on life support. So that's a challenge in the automotive industry. Codethink's view in particular, I mentioned earlier, so we're a software consultancy, we're a services firm, and we have a long history in open source. We specialize in embedded Linux, and we've got a strong expertise in software delivery, lifecycle processes and so on, so build, test, integration, the sort of delivery things that surround software as well. And what this means is that because we're a services company, we work on lots of different automotive projects with lots of different organizations, OEMs and tier ones. And this gives us quite an interesting viewpoint on the industry, I think. And I think it's always interesting when we first come onto a project, we think about things in terms of the theory of constraints. So it's often the case that we'll go onto an automotive project and progress is behind schedule, and people have got an idea as to what's going wrong in order to cause the problems that are delaying things. Sometimes people have got an actual rationale with data to back it up. Sometimes it's just a theory. Sometimes it's just a wild accusation. You know, things can be quite heated and stressful. So one of the first things that Codethink tries to do is find out where is the real pain point in a project. Where is the bottleneck that is constraining the throughput of what we're delivering? Because theory of constraints summarizes this very nicely. It tells us that the maximum capacity of your whole system is constrained to the maximum capacity of the bottleneck. So any improvements at the bottleneck are improvements for the whole system. And in addition to that, conversely, any improvements either side of the bottleneck is a complete waste of time. It's just an illusion. You have to identify the bottleneck, alleviate it, find the next bottleneck, alleviate. And this sort of motorway or highway is a nice example of that, because it doesn't matter that you've got a nice 6-lane big capacity before it. If you've got a bottleneck at one point, that's the entire capacity of your system. So we're looking for bottlenecks. And invariably, we do see the same problems repeating on different projects in the same manner, and we always find bottlenecks in testing of some form or another. And broadly speaking, there are two main ways that we work on testing on projects. One is a concentrated effort to try to bring more testing earlier in the cycle, or better testing, more focused testing, maybe you could say. This is often called shift left, which Magnus mentioned this morning in his talk as well. And then also improving the reliability and robustness of testing. And that is almost always through automation and CI and CD. So why testing matters? Testing is very expensive. Most projects still rely on manual testers. Smaller projects will have teams of tens of people on testing. Most projects, it's in the hundreds in automotive. Some of the large automotive projects, in my experience, you can have over 1,000 people working on validation of some form or another. Testing on hardware is particularly important because hardware is a prized resource, especially in the early days of a project. You know, I'm sure we've all been in that situation. It's quite difficult to get your hands on hardware in the early days. People can, not literally, but metaphorically fight over it. So if you've got a problem in the software, for example, if it doesn't boot, you want to find that in emulation before you even get to testing on the hardware. Because there's no point wasting people's time putting that onto the hardware if it doesn't even boot, or if you have another less drastic but also critical issue. And then we can take that one step further and talk about the testing environment in the vehicle. That is the most expensive testing environment you can have, because the prototype vehicles take ages to get ready at the start of a project, and not everybody has the special license needed to do the testing. So if you're finding issues in the vehicle that could have been found earlier, that's another waste of people's energy. And I think the reason I say testing has these bottlenecks is because there's lots and lots of these hidden costs in testing. The project that I'm on at the moment, if you brick the unit within a vehicle, you actually have to remove the seats in order to go under and replace the wiring. You have to phone somebody in another department and they come down. So again, and then everybody stops what they're doing for a few hours, and your planned day of testing is wasted. So it's a huge cost involved. So we're trying to find as many issues as we can, as early as we possibly can, because the earlier we find them, the less expensive they are to deal with. And then on a similar point, kind of slightly different but related, we're trying to automate as many manual tests as we possibly can, for obvious reasons. It's more reliable, it's more robust, and we can make better use of our time. So one great example, again, the project I'm working on at the moment, when they do a full system validation, I asked the validation manager, in terms of plugging the USB stick in and out, how many times do you test that in a full system validation, which is a 3-week test? Does anyone want to guess? How many times might they unplug a USB stick? Go on, give me one guess. 10? No, it's more than that. It was 800 times. So that's a human being doing that 800 times, right? Over 3 weeks, like I say. And if we give that a very optimistic estimate of 30 seconds per time, which is optimistic because you have to check that it loads and it's all loaded correctly and so on, that's 400 minutes, which is very nearly a full working day. And not only does it cost you a full working day, but it probably costs you the sanity of the poor person who's having to do it. But also, if we could automate that, we could do that overnight and make better use of the hardware, because you're using it, instead of it being unused overnight, it's using something. And obviously, the biggest thing is that person can be freed up to do something much more valuable, much more interesting. They can be stress testing the system or just using it as a user would. So automating as much as we can is of clear value. All right, quick recap on what Codethink has spoken about at previous events. I'm not going to just regurgitate everything, but I will just touch on some of the key technologies that we've used in the past, because it's important to get this kind of grounding in the tooling. So we have spoken before at ELC in 2021 and FOSDEM last year, and that talk was about Lava we used with OpenQA. OpenQA is, I'm sure some people would know it. Oh no, sorry, before we get onto that slide, there's another one. One of the key messages that we put forward in those talks was about what we called the gap. And certainly we're not the first people to have spoken about this. But basically, again, you've got products that are designed to be out in the field for 10 plus years, not just automotive, but all sorts of products. And you rely on, let's say, a kernel version, and that's only supported for 2 years. So again, the life cycle of the product is longer than the supported version. People are wary about doing full system upgrades because of the huge cost and time involved in the regression tests to give you the confidence to do the upgrade. And what this means is that people are then, customers are then missing out on the latest features. And if you speak to the upstreams, their response will usually be, use the latest version. Okay, fair enough. But in reality, there is a gap between upstream and downstream. So we thought that if we could introduce some system testing in open source and make it accessible, we could help to close this gap, right? And system testing is so important in particular because you're not just testing the UI in isolation, you're not just testing that the kernel builds, but you're testing the entire integration in between, or the graphical stack and everything else. Okay, introduction to OpenQA. Some people may know what this is already. It's a pretty well-established testing framework. It was developed by SUSE, for OpenSUSE. So it's designed for testing Linux distros, desktop environments, and it does that in a combination of screenshots and click and assert and timeout values. So what the great thing about OpenQA is that it is mimicking how users actually use the software. So it's using touch events, because when people use software, they're using the IVI screen, right? They're not sat there simulating CAN signals with a canalizer tool. So that's what was really drew us to it. So needles and tests, very quickly. It's a really important aspect of OpenQA. There's not just the tests, but there's needles as well. A needle is a screenshot of the UI that you expect to see, and then also a JSON file which has all the coordinates of that. And it's quite clever. You can do things like mask a certain part of the screen so that in the bottom left or whatever there's a clock, and you know the clock is going to change time, and you don't want that to fail the test. So you can do clever things like that. And then the tests themselves that live in the Git repo, they kind of operate on the needles, so the tests will assert where you want to click and how long you want to wait for and so forth. So with this combination, you can test every workflow on the screen, navigate from one screen to another, etc., etc. Okay, very brief overview of the architecture of how OpenQA works. Like I say, your tests live in a Git repo. which is useful because you can tag them on every release as your test suite grows over time. We've always used GitLab because it's our weapon of choice, but of course this will work with any automation system. It takes the built image and acts as a launcher, starts an OpenQA worker, and the worker is spun up ad hoc every time that you run the tests, which is quite good. The worker can be anything that you need, anything that you can get your hands on, sorry. So a laptop or a Raspberry Pi or a VM. In our case, it's a GitLab runner, which is a VM. And then separately, you have an OpenQA server, and that gives you a couple of things. One, you store the needles there because they can get pretty massive. And separately, you have a web UI which shows you the results, which you can see there. There's each one of those is a screen that's been navigated to, and they're all green apart from the one down the bottom. And then OpenQA, it was always designed to be used in emulation. So with every worker instance that you spin up, you'll spin up a QEMU environment, run your tests in there, and then report them back to the OpenQA server, which again displays them like this. So very, very useful, for example, for a development team that's working on an HMI, you know, to be able to test the UI so quickly in their development. And this is an example of what one of the tests looked like. We pushed this to GNOME. So the GNOME OS project is using this in their testing. And as you can see down the middle there, there's like an orange line. You move that left and right, and you can see what the screenshot really looked like in reality versus what it was supposed to look like. So it's very, very useful if you have a failure. You can see exactly where the UI has gone wrong. Okay, and this is being used already. Like I say, we've got an OpenQA instance, .gnome.org. Okay, so we've heard a lot about virtualization. This is testing and emulation, as I said, which is really important to help speed up the development loops. But ultimately, we are interested in testing on hardware, particularly non-functional requirements and things like that you're not going to catch in emulation, and a whole host of other reasons. That's where Lava comes in. Again, most people probably know what Lava is, but very quickly, it describes itself as a CI system for deploying operating systems onto physical and virtual hardware for running tests. So it's essentially hardware orchestration for physical devices. You can often have what's called a board farm, where you have loads of different boards connected with different architectures, and Lava will help you flash your latest images and deploy your test suites onto them. And it's used by the kernel CI project. So it's really useful, Lava. What we were able to do last year was get OpenQA working with Lava, so we could run the same tests that we did in emulation, where we were testing the UI, then running on a board with a display and checking that. And again, that's being used. We've got these Codethink instances here, lava.codethink.co.uk and openqa.codethink.co.uk. And we're actually testing the Linux kernel mainline every night. It runs on emulation and on hardware. So yeah, that's an example of this test. It's being used. We had some nice feedback from Linus, which was great. And yes, like I say, we did all of that, testing on emulation, testing on boards, but really the next step was we wanted to be able to test on actual representative hardware. For our clients, we wanted to be able to put these kind of tests onto rigs and so forth. And that's where the new advancements have come in since we spoke last. So I'll hand you back to Daniel.
Thank you. So before I get any further, whenever you see a QR code, it's a web address. If it's in the same place on the same slide, it's the same web address. You don't need to keep taking photos of them. So what is Q.A.D? Q.A.D being the thing that we really want to talk about today. It's a small daemon designed to be able to run on real representative hardware. It's open source, and it's newly released. I think we finally open sourced it Friday?
A week ago, yeah.
Yeah, about a week ago. Okay. It's designed to work on any Linux system. So I'm being quite specifically here. You're not going to use this on QNX yet. Which consumes input events from the Linux input subsystem and works with displays via Wayland. Laurence, do you want to turn yours off? We're too sensitive. Q.A.D. is designed to be minimally invasive, so it uses technologies that are typically already found in IVI systems. So, like I said, the Linux input subsystem, it uses ILM for dealing with the Wayland screens, and it's fully open source. Development is now in the open on the Codethink GitLab.com presence, which we call Codethink Labs, and I encourage you all to take a little look. What it can do is to provide access to any number of displays that are attached to the device and take snapshots of those. It can send input to the input subsystem, and then Linux gets to pass that on to your applications. Those might be touch events with location, they could be swipe events, all sorts of things. And all of this is provided over a fairly simple HTTP API. With the power of those screenshots and those input events, you can use Q.A.D. to grant remote access effectively to your hardware rigs. That permits developers to interact with physical hardware, to potentially run builds on that hardware, whether they're right next to it, at their desk in the office, at home over a VPN. In theory, if you have a VPN to a vehicle, you could use Q.A.D. in the vehicle as well. There are minimal dependencies, like I said, and the non-invasiveness, which means that you can basically plan to design Q.A.D. into your development builds or potentially even into the production builds of your system software without worrying about it being huge or anything like that. But it only provides input to the display and to the input subsystems. It's not a remote shell service. If you're used to having a remote shell to your rigs, continue to use SSH for that. It does not automate any control actions. That sort of orchestration is an external service. And so, thanks to that HTTP API, it's really easy to integrate into an external automation service. So the screenshots allow you to verify that the actions have taken place, and this is, in essence, a trivial encapsulation of the OpenQA methodology. So we've also provided in that repository a patch to OpenQA, which enables OpenQA to consume Q.A.D. rather than expecting to talk VNC to a QEMU. So this diagram that we had before, let's recap. We had OpenQA orchestrating tests using Lava to manage a farm of systems that have been customized for testing purposes. So they were accessed via VNC. This permitted OpenQA to run tests by acquiring a system, running its screenshot and input event processing, and then releasing that board back to the pool to be used later. If instead of a Lava-managed set of VNC-enabled development boards, we instead want to have an actual automotive rig, then production ECUs, all of that, we would be running tests in a much closer to production vehicle environment. And that can be really, really important, as Laurence mentioned, particularly with respect to non-functional validation. But we're left with a gap. We need to bridge OpenQA runners to the hardware, and that's where Q.A.D. comes in. This is a setup which approximates our approach on an existing engagement with an automotive client. First, we have to boot the right system on that rig. And this uses another device that we've developed. It's open. I'll talk about it later. To ensure that the appropriate software build is on the rig. And then, once we've ensured that that software has come up and it started Q.A.D., then we can use Q.A.D. to run the tests on that rig. That means that that test is running against real ECUs, which massively increases the scope of possible testing that you can run and expect representative results from. So with all this in place, you've got a robust, reliable, rapid, systematic test framework for target ECUs to really build that confidence with your final system tests so that you're much less worried about making more releases, which, for SDV, kind of important. So what's an open source conference without a janky video? Let's give it a go. I have no idea if this will work. Hooray. So here we've got an example rig on a developer desk. It's actually a Raspberry Pi, but don't tell anyone. On the left there, we've got a setup, and on the right, an OpenQA worker. On the left now, you can see an event trace, and on the right, Q.A.D. is running. We launch an OpenQA test pretending we're a CI runner, and we can see that the test has started there on the right. This test presses the HVAC button. The screen changes. These were the input events that were sent. You can see that happening in real time. A screenshot is taken. We then press the home button. input events for the home button. And again, a screenshot is taken. All of that is then processed and uploaded to the OpenQA server. The OpenQA server refreshes. We can open that up. Looks fairly familiar. And we can see the 3 screenshots that were taken. So the initial home screen, the HVAC screen, and then back to the home screen. And so obviously if there were problems with those, those problems would be highlighted, but this test passed. So we're all good. Laurence mentioned needles. The common way to build needles for OpenQA testing is you write a test and it fails because it took a screenshot and it didn't match there was no screenshot. You then go into the OpenQA server and you click around and you highlight stuff and you build your needle, and then you run your test again and it gets a bit further and then it fails. It's effective, but it could be improved. And again, within the Q.A.D. project, we're working on improving that workflow somewhat. So this is pre-release. We've not actually put this out yet, but it will be released as soon as we've solved a couple of little UX issues and written enough documentation that we can expect someone else to use it. The Q.A.D. web UI is effectively a remote rig, so it gives you something close to VNC experience with a rig that's running Q.A.D. It helps to streamline the screenshot gathering and needle creation process. Is that the? Yes, it is. So you can see here the current screen on the rig. So you can take a screenshot, you can then configure a needle, and you can save it into your needle set. And the concept here is that you save that needle into a Git repository. The server also has that Git repository checked out, so it can retrieve the needles, and thus you can get through that whole process a lot more quickly. As mentioned before, the web UI is in development at the moment. It'll be released once it's in a reasonable state. But because of the nature of Q.A.D. and using all of that, we would hope that people will be pretty quick at adopting it. We're also developing different input subsystem support. Some of you are probably familiar with the fact that for some reason automotive companies like to define their own mechanisms for processing input that aren't just the Linux input subsystem. So we need to be able to handle those. And we want to add some more screen capture backends. At the moment, we only do ILM. But I believe one of our engineers has a pure Wayland, or at least a Western capture working. So we're going to get somewhere with that. We're also developing other kinds of input device event support. So like I said, at the moment, simple touch works, basic swiping works. We'd like to add multi-touch events. We'd like to add complex press, hold, move, things where you can take screenshots in between, that kind of thing. All of this is open source. Q.A.D. itself is under the MIT license, so that should be the most trivial thing for you to be able to integrate. The OpenQA patches are under the GPL v2, I think, because OpenQA is under GPL v2. And we'd love your help to make this work on your own hardware, because the more things it works on, the more opportunities there are for getting good testing to happen. I said that we want to be able to then write more tests. You can expand your test repertoire because you're now running on representative hardware. And at Codethink, we'd like to be able to do that as well. We want to develop either additions to Q.A.D. or other tooling and other devices to aid in testing real representative hardware. And one example of that is we'd really like to reduce the dependency on having proprietary CAN tooling in your automated test rigs. Who here is familiar with something like Vector Canalizer? A couple of hands, okay. It's quite a complex tool, but it's really powerful. And that power, frankly, belongs in the hands of an engineer doing work, not running on its own laptop, attached to a rig, in a rack somewhere, hidden away, running tests all the time. So we're working on enabling an open source equivalent of that is actually presenting CAN frames on demand in the right way, integrated into your OpenQA testing. And to ensure that we keep doing this open, rather than just for whichever client comes along, we really hope members of this community might be interested in engaging with us and getting a bit further. I briefly mentioned on the slide where I talked about getting software onto a real rig that you needed a device to do that. This is an example of another open source project that Codethink is involved with. This is a mechanism for attaching and detaching USB devices and USB hosts. It's a switch, right? It permits constructing automated test flows which, for example, change which firmware is on a rig by swapping different USB sticks in and running updates, or allowing you to attach mobile phones to a rig and testing mobile phone projection, that kind of thing. And as a sort of benefit, because we were asked to, it can keep devices powered. So if you've got a rack and you've got an iPhone and an Android phone plugged into this, they're not going to run out of battery just because you're not running tests for 6 hours. Although hopefully you're running tests all the time. Being a bidirectional switch means that it can be used in lots of test scenarios. I mentioned the phone projection one. I mentioned USB sticks. That's 2 hosts attached to one device, switching between the hosts so that you can attach it to your test controller, which is then going to write a firmware update to the USB stick, and then attach that USB stick to the rig to allow the rig to perform an upgrade. It's open design. The hardware is fully open. You can download the Gerbers. You can send that board off, get it built. All of the placement, everything is there. The firmware that runs on this unit to enable it, all of that is open. The control software that you can run on a PC, that's open. Heck, even the 3D printable case is open source. Please, just it's less than $100 to make one of these, and you should have about 1,000 of them in your life. Okay, it's probably enough advertising my favorite open source project, but just in case, it is real. I've got one here. You're welcome to come and look at it and go, oh, yes, that's not doing anything, if you're really interested. Laurence.
Okay, thanks. How are we doing for time? All right, so to summarize then, we spoke about software complexity, we spoke about bottlenecks, and closing the gap, and we spoke about how expensive testing can be. So the takeaway is that automating that testing is a challenge, it's difficult, but with the right tooling, it is much more achievable. And importantly, if the tooling that you choose is open source, it can be cost effective as well. And that's what we've been thinking about quite strongly for the past couple of years. We did a lot in the open. We've worked with the client to do it, so there's some very real applications of this work. And we're open sourcing everything as well. So yeah, it's something that Daniel and I are pretty passionate about, and Codethink in general is passionate about, and we're always willing to talk about it. So if you have any questions now, we're very willing to take those, and we're very willing to talk about it afterwards, over a drink maybe, because it's the afternoon. Thank you very much.
Yeah, so the connectors on this are USB-C. The control interface is it's USB 2 on that connector. My understanding, and I'm saying this as someone who wasn't directly involved in the very core hardware here, is that it supports switching both the full speed lines and the super speed lines. I believe it's set up in a way that is supposed to pass through the control signaling, but there are some complexities involved in trying to do that and maintain power to devices when they're not, actively in use. I would not expect it to, for example, pass through power delivery. I think that might cause the board to explode. I'm not sure. But, it's an open design. If you can come up with some fixes to make it even better, then merge request gratefully accepted. So the question is around multi-touch and how to make that work. At the moment, I think the device that's in the project that Laurence is dealing with, the touchscreen is actually a multi-touch touchscreen. And that comes up in the Linux input subsystem specifically as a multi-touch device. Q.A.D supports creating a multi-touch transaction, adding touch points to it, processing those touch points and so on. But at the moment, we don't have a mechanism within the actual API that it exposes to make that happen. My expectation is that it will end up being a multi-operation API. So it may be, I'm going to either submit an entire thing that says, here are 5 touch points, and you're just going to go touch point, or it will, because swipes and multi-touch operations tend to be gestures, it's almost certainly going to be a case of enabling, starting a multi-touch transaction, performing some operations, closing the multi-touch transaction as multiple API calls to Q.A.D. But I'm not in charge of that API, so I could be wrong. And again, issues and merge requests welcome.
I think it's definitely possible. Since we started this, we added swipe and scroll, which are very similar, of course. Scroll is just a slower swipe. And we're just now adding pinch to the map, which was more difficult than we thought. But I think the API is pretty decent for OpenQA. So multi-touch is on the list. We haven't got around to it yet, but I think we think it should definitely be possible, yeah.
Well, thank you very much.
All right, thanks.